Welcome to the AP Calculus BC video for skill number 206. I can simplify and solve both exponential and logarithmic expressions and equations and translate between bases. Alright, we'll start our notes on page 206A, and the first thing I wanted to show was the conversion from logarithmic to exponential. And this is something we should be comfortable with. But if we have log base b, so any base of x, and that is equal to y, we can rewrite it in the terms of b to the y is equal to x, as shown over here. I've also shown it for the natural log, and remember natural log is just log base e. So if we were to rewrite this in exponential, we would have e to the y is equal to x. Next piece is the change of base formula, and anytime you have a base that you would rather be using a different base on, you can change it by taking log new base, so log base b, whatever you want it to be, of the argument, the x value, over log new base of a, your original base value. Most often people just take the natural log of x over the natural log of a, because when we're operating in e, that is very useful at times. So that's why we lean in that direction. Next up we have the properties of logarithms, and there's three key properties. The first one is if you have two logarithms being added together and they have the same base, we can rewrite it as log base b of the two arguments multiplied. If we're subtracting the logarithms, then we can write it as the arguments divided. And the last one that pops up a lot is when you have log base b of a raised to an exponent, we can drop the exponent down in front so that we get exponent times log base b of our argument. One last property is the base or log base b of 1 is equal to 0. So it doesn't matter what your base is. You could have log base 7 of 1, that equals 0. The natural log of 1 is equal to 0. And that fact is useful if we want to use it for graphing. I like using it because it calls out that one point where regardless of the base, your logarithm is still going to cross at 1, 0 unless you've transformed the function. Inversely, the exponential will cross at 0, 1. Alright, so the most elementary type of problem from this section is to express as a single logarithm. So there is an expression that has multiple logarithms and we want to change it so that it's a single log. So in the first step, I took any numbers in front of logs and turned them into exponents. I did that on this one, and then I also moved the 5 up. And then in the second step, what I did is I combined the addition logarithms to get that. I also distributed the 5, which isn't entirely necessary, but I like it that way. And then in the final step, I took my subtracted logarithms and wrote it as a quotient, log of your first argument divided by your second argument. Alright, for example 2, it says solve each equation, and this is more in line with what I think you should be able to do. What I've got here is log of 6x minus 4 equals 2, and very common if you have a single logarithm, the easy path to solve for x is to write it into exponential form. And so what I did is I converted this problem stem into an exponential statement. And remember, if the base is not written, it could be considered base 10. So what we have is 10 squared is equal to 6x minus 4. And now we've turned it into an algebraic problem that should be pretty easy to solve, and I arrived at the final answer of 17.3 repeating. The next example below, what we have is there are two logarithms, so we should be combining it into a single logarithm using our properties of logs. And make sure we have the same base. So the first thing I did was I combined them into a single logarithm. I took the two arguments that are being subtracted and wrote it as a quotient. And now we can do what we did on the last problem, which was write it in exponential form. So we have base 3 raised to the fourth is equal to your argument. So 3 to the fourth is equal to the argument. And now it's a algebraic problem that we can solve with our algebraic properties. 81 equals 2 over x. I had canceled an x out of top and bottom, and then I solved for x. And there we have an approximate value. Okay, for example 3, solve each equation. This time we started with an exponential equation rather than a logarithmic. So sometimes it's useful to take our exponential equation and convert it to a logarithmic expression. So I did that, took the exponential and rewrote it as a logarithmic. And if you want to check, you have 5 to the 2x plus 10 equals 3, and that's our expression. Normally log base 5 of 3 you could not type into a calculator, so people would convert the base. You're able to do it now, but if we wanted to get an exact value, I like to have it converted to base 10, which you can see I did here. But in all reality, we could have left it as base 5 and then subtracted our 10 and divided the whole thing by 2. That would have been a completely acceptable answer as well, and I would have accepted it. There's lots of different ways you can represent logarithms. Here's one possible way, the one that I worked through first. Alternatively, you can start by taking the log of both sides, which is what I did. So I've shown you 3 ways to do this problem. Take the log of both sides. Oops. Log of that, and then what we have is an exponent that we can drop down. And then we divide both sides by log of 5. And we arrive at the same answer as we had above. There are a couple different ways to tackle the problem. I don't mind which way you choose to do it. Alright, this concludes skill number 206 for Calculus BC. You should be able to simplify or solve exponential and logarithmic expressions and equations. And you should also be able to translate between bases.